I would like to introduce Nicolas Marin, Director of Hardware at Quandela, that will take the second part of the presentation and that will show you how we build the quantum computer.
Hi everyone, my name is Nicolas Marin, and yeah, indeed, part of my presentation I will show you how we go to low temperature and what is at low temperature for us. So during this, I hope you can hear me well, by the way.
Yes, we can hear you. I can also see your slide, Nicolas.
Cool. So in this presentation, I will show you what's a bit on the hardware side of Quandela. How do we build our photonic quantum computer? So my name is Nicolas Marin. I have a background in experimental quantum optics. And I joined Quandela a bit less than 3 years ago, where I mostly work on the hardware side, so putting online this Ascala hardware that Arnaud was mentioning, and also delivering a quantum computer fully integrated. So these are the mainly two parts I will talk about, and so to show you the different optoelectronics modules that composed the platform, try to connect a bit with what was said on the theory part, and yeah, realize what is behind it and the engineering work that was done in the last years. So just as another introduction of digital quantum computing, so we are quite used to these matter qubits, so this platform where you have like superconducting qubits, ions, neutral atoms. These are very easy to represent to ourselves. So these are visible qubits, they don't move, they are matter qubits on chip, for example, where they interact together close to each other. And what we use are photonic qubits. So this is quite different. We have actually photons that are said flying qubits. They move, we don't see them. And the good part with that is that we can control them and connect them together with fiber optics that is widely used, for example, in the telecom, and manipulate them with photonic circuits. And they are quite robust qubits. They don't see decoherence, and as what was mentioned, the main drawback is losses that we have to fight, and this is an engineering problem that I will mention again. So what is the main architecture of our platform? Mostly we need to generate these photonic qubits using single photon sources. Then we need to manipulate an input state using an optical circuit. And finally, we need to do a measurement. So this is really the three parts around it. You have software, electronics, readouts, all these layers around, but the main three hardware modules is the photonic generation, manipulation, and measurement. And so actually exactly 1 year ago, we put online Ascala on cloud. So this is a machine. So at the end of this talk, you will understand this setup, and also be able to read this paper that we published last year and go maybe deeper into the subject. So mainly what we have in this machine is this single photon emitter, quantum dot single photon emitter. So there are several types of single photon sources. One which is widely used is set parametric sources or probabilistic sources. Mainly what it consists of is to shine a laser into a nonlinear crystal using several processes, so spontaneous parametric down conversion or spontaneous forward mixing. And this is a probabilistic process. And what happens is that one or two laser photon will be converted into will be split into two different single photons via conversion nonlinear conversion process. And what they are heralded because one photon that is, let me try to get the laser pointer. I don't know if you see my
we see it, Nicolas. We see your mouse.
Thank you. So one photon that is detected in one mode will herald the other, the presence of another photon there. And physics tells you that the brightness of the source has to be extremely low to keep the purity high. So this is the main limitation there. And so what we use is another type of source. It is single emitter sources. In our case, a quantum dot in an optical cavity. And there, these sources are set deterministic because, in principle, when we ask for a photon, we can emit one. And in particular, what we use is indium gallium arsenide quantum dots. These are very small semiconductor structures that act as an artificial atom, meaning they have a discrete optical transition in which the energy difference gives you the wavelength of the emitted photon. So when we shine a laser, it spontaneously spontaneously emit a single photon. Main issue there is that these photons are emitted in every direction. So what we use is cavity quantum electrodynamics theory, where we put this quantum dot in the middle of an optical cavity where you have a mirror on top and a mirror at the bottom. And what it does, this cavity, if you engineer it well, it accelerates the spontaneous emission of the single photon using the Purcell effect. And if you do things well, you can increase a lot the mode coupling, so the emission of the quantum dot, with the mode of the optical cavity, and which will make this quantum dot emit only in this mode, as well as the outcoupling efficiency, where you can make the quantum dot emit only in one direction. So here we would like to emit from the top of this cavity. So in practice, what we do is to shine a laser on the top. We couple a laser into this cavity, and the photon will be emitted backwards. We even have a small animation to show quantum dot emitting everywhere, all direction, and we improve the emission probability into one mode. And what the nice thing with these cavities is that their mode look very similar to an optical fiber. So it's really easy to couple this photon into an actual fiber that's represented here in yellow. So these devices are maybe the core technology of Quandela. This is why Quandela was created. So from the group of Pascal Senella in CNRS lab, where she really made many years of research on how to couple these quantum dots into a cavity and improve the performances with state-of-the-art performances in terms of the different metrics that I will present today. So an ideal source, obviously, is an ideal single photon source emits a photon every time we ask for one here. Reality is different, so we have losses, so we can lose photons on the way. This is what we call the brightness or the efficiency of the source. How many photons do we get compared to how many times we ask for one. We can sometimes see multiple photons at the same time, 2, 3 photons. So this is a source of error that we try to mitigate. And the third one is this indistinguishability, how the photons look like to each other. How well do they look like? Do they have exactly the same wavelength, the same lifetime in every degree of freedom? And this is extremely important for quantum interferences, which is the basis of the calculation here at Quandela. So few experimental tricks. How do we measure the photon purity? How do we measure that we have only one photon for every pulse? this is the Humphrey-Brown twist experiment. We input a single photon into a 50-50 beam splitter, meaning you have a 50% chance to be transmitted, 50 to be reflected. And you put two different detectors, and you measure the coincidences between these detectors. And if you have only one photon, these detectors, in principle, will never click at the same time. And this is what you see here. This the measurement of the second order autocorrelation measurement, where you see peaks because we excite the source every 12 nanoseconds here. And if you look at the number of coincidences that you have at time 0, so the time difference between the detector, you will never see any counts, meaning we have a very pure single photon. Now, how do we measure indistinguishability? How the photon can interfere together? What we use is the Angou-Mandel effect. So we send two single photons together in each input of the same beam splitter now, with 50-50% chance of reflection and transmission. And what you have is the extremely simple or the most basic quantum interference you can find with two single photons is the Angou-Mandel effect. And what it does, quantum physics tells you that the single photons will always exit the beam splitter together. So photons like to be together, and what you will measure is very similar measurements. No coincidences will happen at the same time, because the two photons will be detected by the same detector. And what you actually create is a very simple, like entangled state where you have two photons in one mode and 0 photon on the other mode. And this metric is the what we call the HOM, or indistinguishability. It tells you how well the photons are overlapping each other in every degree of freedom. Can be the wavelength, the time, spatial overlap as well. So this tells you how well you can interfere them. And so today at Quandela, I give you mainly the main characteristic of these single photon sources that we have. We emit single photons at 928 nanometer wavelength with lifetime below 100 picosecond. The purity, so how well the single photon mode is, and how the metric that tells you that we have only one photon per pulse is shown by this purity, more than 99%, and indistinguishability above 94%. With, very importantly, the polarized brightness, so the efficiency of the source, which is today approximately 50%, but that can be pushed further to 100%, towards 100%. And we need to cool these down at 4 Kelvin, so close to the absolute zero. And I will show you later what kind of cryostat do we use. And so Quandela is really at the state of the art today of this single photon source performances, where here we plot brightness and indistinguishability, and we are really at the top of this area. And so qubit encoding, I think Arnaud already told you, but there are many ways to encode a qubit in a photon. So again, these degrees of freedom, we can use the frequency of the photon, the orbital angular momentum. Very famous encoding scheme is the polarization. And today, in the version of the platform we have today, we use path encoding, where the qubit 0 is, for example, a photon being on the top path, and qubit 1 being the photon being on the lower path, for example. So you can represent your state with this block sphere, and you can go all around the block sphere using, for example, a beam splitter, superposition of beam in the top and bottom path. And using a Mach-Zehnder interferometer and some phase shifter. So a very simple interferometer. Here you can really position yourself anywhere on the Bloch sphere. And so any quantum gates can be translated into an actual optical circuit. And I think this is what Arnaud was showing before. So now that we have single photons at the output of this cryostat, we want to actually send many of them. So here, for example, 6 of them into this universal interferometer that will implement the optical circuit that the user wants to sample. But before that, we need a demultiplexer stage where from one stream of photon at the output of the single photon, we demultiplex to get many inputs at the input of the interferometer. And what we use is a very fast deflector. So we take one photon, we send it to one path, the next one to the other, etc. So we need a very fast switch. I can give you the example of what we use. We used in Ascala. This is an acousto-optic modulator. Basically, this is a crystal in which you send a very fast sound wave at approximately 200 megahertz. And this sound wave, what it does, it will give you a grating with oscillation of the refractive index in the crystal, and which will diffract an input optical beam. So if you change the frequency, and so the angle of diffraction, will be a function of this frequency of the optical wave. And so if you change quickly the frequency of the sound waves, you will basically create different diffraction angle. If you do it quickly enough, you can basically switch between several modes. And the speed at which you can do this is defined by the speed of the sound wave that travels along the optical mode. You have to go to have a small optical mode inside this crystal and a fast sound wave. So this is the setup we use. You see on the bottom left the optical acousto-optic modulator that will be sent into this very small mirror to catch the different diffracted beams, and then sent back into optical fibers that you see here in blue. And so something I'm not showing are fiber delays that we use to synchronize then the different photons. So now I will go through this like unitary transformation capability that we have, or a universal interferometer. So what we use here is a 12 by 12 reconfigurable universal interferometer that can implement any 12 by 12 unitary matrix. So in our case, we have up to 6 photons that we put into every odd input of the interferometer, again for path encoding capabilities. And at the output, we can detect all to sample the outputs. And so what's this interferometer? It's basically many beam splitters, 50-50 beam splitters that you see here. These are the waveguides or the optical path, and each blue box are phase shifters that can be controlled remotely. And so what we use for that, this is a very complex circuit. We don't use free space optics. We use integrated photonics, and this is mostly the same revolution that we have experienced for electronics, where we went from bulky electronics to very integrated systems. And so in our case, we use this to miniaturize a lot the optical circuits and elements. It also gives you a very good mechanical stability because everything is compact and monolithic. And in practice, what we use is very small structures in which you control very well the refractive index of the material to confine the light. Here, for example, for silicon nitride waveguide, where you have the simulated optical mode in the middle of the waveguide. And the light can be really confined, and you can really make your circuits super small. I will show you how to make a beam splitter using this. We don't have mirrors in photonic integrated circuits. We only have waveguides. So here you see the cross section of two different waveguides, and the point here is that you will, if you do your mode calculation there, how the light is traveling there, you will always have a bit of light outside of the core here, defined by the refractive index N1, and you will always leak slightly some light at on the neighboring waveguides. And so the idea of doing a beam splitter is to put two waveguides very close to each other, and via called evanescent coupling, you will couple some light from one waveguide to the other. And if you make this interaction length, if you control well the interaction length between the two waveguides, you can control the ratio at the output of the beam splitter. So from one port, you can have 50-50 chance, a 50-50 coupling. And a second element that we have on the interferometer are thermo-optic phase shifters. So these are some types of phase shifting capability, and the idea is extremely simple. You put some resistor on top of the waveguide. You input some voltage. This will slightly warm up on top of the waveguide, and the refractive index of the mode is dependent on the temperature, and you will change slightly the speed of the light traveling through it. And in our Quandela, we have 126 of these thermo-optical phase shifters and 132 of these directional couplers. Basically, the process here from a circuit, we have the compilation process where we calculate what is the phase, the set of phases that have to be applied into the interferometer to apply the unitary matrix that is needed by the user. And then we have a transpilation stage in which we go from the set of phase that we want to apply to the actual voltage control. What are the voltages that we need to implement on chip? And this will also do this by taking into account the different imperfection that we have on chip and the different crosstalk, because when we apply a phase or voltage onto one phase shifter, it actually warms up locally, but also outside of the waveguide that we want. So it gives a lot of crosstalk between the different phase shifters. So we take this into account in the transpilation stage, where to apply from phase to voltage is set, and the calibration was done using machine learning techniques with very high fidelities. To end up the setup, we finally have detectors. In this case, are also cooled down at 4 Kelvin in a cryostat that you see here. This is the cold head of the cryostat inside this chamber. And what you have inside is single photon detectors that are called supraconducting nanowires. And the idea is also very simple. You have looks like also like an integrated photonic circuit, but here you have a nanowire that is the supraconducting material. And on top of this nanowire, I'm not showing, but you have a fiber on top that is where you have also a cavity coupling inside this system. And the idea here is if a photon is detected, or if a photon is absorbed by this nanowire, you will get a hotspot formation here, and this nanowire will become obviously resistive. And what you measure is a peak of voltage. What you have is a peak of voltage that you can actually detect. So from zero resistivity to high resistivity. And these are great systems. They are actually commercially available with extremely high detection efficiencies, so above 90% detection efficiency, and really low jitter. So you can detect in the order of 30 picosecond detection resolution. And so we have at the output of a scala 12 of them. You see the fibers at the input of the cryostat and the electronics cable that will then give you all of them this voltage peak. And these will be digitalized with electronics, what we call the time tagger or correlator. And that will be the result of the sampling that a user can implement. And so the main characteristic of the main metrics that we have on La Scala, one very important one is the efficiency. And this is doesn't look very high, but it is actually a state-of-the-art experiment. So close to 8% efficiency total. And this allows us to actually measure up to 6 photon coincidences. And you see how very fast this decreases. So as was discussed before, this is mainly the goal is to reduce these losses, to go to higher number of qubits, higher number of photons, and improve these coincidence rates. You also see the engouement Mendel, the indistinguishability measurements, purity, and also the CNOT fidelity that is also always measured via cloud. I will not come back to this. This is what Arnaud mentioned. We benchmarked our system compared to the other cloud accessible platform. And so it's been exactly a year that the system is running. So we keep monitoring the system. Actually, every hour we go and recharacterize the system. These are measurements that you recognize: the G2, HOM, the CNOT fidelity, and the efficiency, or what we call transmittance of the system. And so every hour we do a characterization, we check that the system is doing fine. This is over, I think, a 2 months period, what I'm showing. And we also re-optimize the system. So we have a very stable, intrinsically, we have a very stable system, but some stuff can move. For example, the polarization and fibers, the source stability. So we re-optimize the different parameters in every element or different modules that we can to keep the performances super high. So this is how we can get very close to 100% availability when the system is running. So this is how it looks like in the lab. I introduce you to Andreas. He's a PhD student with us working on the platform, and is so to show you the scale a bit of this of the system. It's a bit spread out everywhere. It takes a lot of space. You recognize the SNSPD system on the left, so the single photon detectors. Here you see what I didn't show, the cryostat that we use on this optical table. So the gray box at the bottom is actually the full cryostat, takes a lot of space. So you have optics on top. Should have put a picture, but you have optics on top to access the single photon source. You have the demultiplexer box here and the photonic integrated circuit there. And so we recently had a client who wanted a fully integrated system in their data center. And so we had to do this work of engineering to go from a lab setup to a fully integrated and data center compatible setup. And so we redesigned a lot of the different modules that I was showing, not entering into too much details, but mostly we redesigned the full electronic architecture to drive by, for example, all the different optoelectronic systems ourselves without lab components, basically. And so we have several drawers there where you can recognize here a photonic processor, the filtering and demultiplexing stage. So everything, we try to make everything more compact. It's not, we haven't finished the full work of compactness. Everything is not yet fully in photonic integrated circuits, but still these are very stable modules, optoelectronics modules that are in this 19-inch rack standards. More importantly, we have a new helium compression system, so a cryostat here on top with a compressor that compresses and expands the helium liquid that will work basically like a fridge, so compress the helium on a cold head in a very small volume to extract the heat and cool down finally up to 2 to 3 Kelvin. One device that we use was also developed by Quandela. This is the single photon source, but with a very nice package where you have a fiber that is directly connected to the top of the optical cavity that I was showing before. And this makes an extremely compact device where you see the fiber right on top here. It's quite transparent, but I think we can see it. And that collects directly the single photons out of this cavity. And what we showed is quite very good also specifications or performances of this device. And what we integrate, so it's very compact, so we can integrate it in very compact cryostats. Here what you see is the actual cold head that is at 4 Kelvin when everything is closed and pumped and cooled down. And this is the installation. You have the pigtail single photon source inside this square shield with around the single photon detectors that are all around the system. You have 6 of them here. These are also extremely small chips connected via optical fibers right on top. This is the view of the cryostat from the top. So you have the chamber here that is pumped, so vacuum pumped, and then cool down. And you see all the different wires that comes. These are for the supraconducting nano wire detectors that gives us the detection signal. Okay. I can show you also the photonic chip. This is a small photonic integrated circuit that is packaged. You have the fibers input and output here on the chip, and all the electronics control, so the different phase shifters that are actually controlled by also a Quandela driver, and a lot of different electronics. What you have here, for example, is polarization control of every fiber at the input and output of the chip. Is the video going to show? Yes. So what you see is the full team actually building the system. This is a quite good video that we mostly worked on in the last year. So you have the cryostat at the bottom and people around, like mounting the different modules that have been produced, laser systems, optoelectronics, the PIC modules, and everything. So this, we are quite proud of it. So this is the moment where we celebrated and show you the full team of people working on this. It can be on the electronics, optoelectronics, optics, semiconductor team, software, So many people working on this kind of projects. Okay, so takeaway, I have shown you the different parts of the photonic quantum computer, from the single photon source to the multiplexer, photonic chip, the detector. So now you can also build your quantum computer and show you the different challenges to go from which are not over, to go from a prototype in a lab to a product fully integrated for data centers. So the goal and the next steps are mostly to improve a lot the efficiency and the transparency of these modules, to improve the capability, add more photons, add more capability, for example, generation of directly cluster states and entangled states from the single photon source. So a lot of challenges. So thank you very much, and if you have questions, we'll be happy to answer.
네, 질문 있으시면 thank you, Nicola, for the presentation. 질문 있으시면 질문해 주시고요. 아까처럼 채팅방에 올려주셔도 체크하고 답변 드리도록 하겠습니다.
So I did not catch that.
No, I spoke in Korean to audience that we are taking the questionnaires. Yeah.
Okay.
Okay, if you don't have question for Nicola, we will stop there.
I have a simple question. Is it possible that two distinct qubits interact with each other? For example, qubit 0 and qubit 4 can interact with each other. I'm just wondering.
So the photonic chip is actually done for this. It's large enough that you can really direct the photon 1 with 4 or up to 6 together and make them interfere. If I understood the question.
Yeah, so it's connected to the unitary matrix that Shane was presenting yesterday. Whatever transformation you want to make, so interfering the photon 1 with photon 5 is just a unitary matrix. So at the end of the day, there is a all-to-one connectivity in a photonic chip thanks to the unitary matrix application.
Okay, thank you.
네, 추가 질문 있으신가요? There's one in the chatting room. Actually, written in Korean mainly, like from the energy consumption perspective, can you compare regarding that's in English?
Nicola, this one is for you in the chat.
Yeah. So comparison between so the temperature at which we are operating the single photon source and the detectors for Kelvin is really not that cold compared to other technologies like supraconducting qubits. And actually, this cryostat, in which we use to cool down, is only consuming, I think, close to one kilowatt of power, and this can be plugged into a household electric plug. And when you compare to this huge dilution fridge that you need to go to millikelvin temperature, this is extremely, I think it's probably 10 times lower than what is used in other platforms.
In terms of scalability, it's something that we didn't touch in this presentation, but what is quite neat with the system that we are developing is that one single source is able to emit 1 qubit, 2 qubits, n qubits. There is no limitation. We don't need to add a new source when you want to add up new qubits. So scalability is relatively easy. The only bottleneck is transmission again. If we are losing too many photons, then we won't be able to reach 100 qubits. So the scalability is very easy as long as we maintain the transmission under control, which is a very technological challenge. So if we have no more questions, so I would like to remind you, so thank you, Nicolas, and thank you everybody to attend to this course. I would like to remind you that the next session will be in 3 weeks, and we will have the honor to have Professor Quandela as a guest that will explain us what is the physics of the quantum dots. We will talk about applications, how to make application with this technology, and we'll also make some benchmark between photonic quantum computer and other technologies, so how we can evaluate precisely the two different technology. And this will be over for this type of class, and after in the next year, at the beginning of next year, we will continue with a Perceval class that will be a programming class where you will have access to our cloud. We'll give you credits to make some computation. You will get some either on QPU or on simulator, large simulators. And in the meantime, if you have any questions, so keep them, and we will answer them at the next session. So thank you very much to everybody.
Yeah.